next speaker is going to be Lucia Ayala. She's an art historian who specializes in reciprocal relationships between artists and scientists, mainly in the context of modern astronomy and contemporary astrophysics. In 2011, she, just last year, completed a PhD in art history as part of a program between Humboldt University and the University of Granada. From November 2012, currently she's at the Vienna Institute for Applied Arts. And in November of this year, she's going to take a postdoctoral position in the Office of History of Science and Technology at Berkeley. So, you can tell us about your topic.
Can you hear me? So, better so?
Yes.
Yes. Okay. So thank you very much, Mike, for the invitation. And as an art historian who studied in Germany, I'm going to read my presentation. We are celebrating the first centenary of Slipher's observation of the radial velocity of nebula. That is, the first evidence of a high velocity displacement of the nebula and the subsequent importance of this discovery when it was used to confirm the existence of galaxies beyond the Milky Way and the expansion of the universe. In the popular opinion, Slipher's discovery, together with a further step taken by later scientists like George Lemaitre and Edwin Hubble, is seen as a sharp borderline that initiated the contemporary understanding of the cosmos. After these pioneering works, humanity finally seemed to comprehend the real structure and functioning of the physical world we live in. To us, it's very strange to conceive how until these years, just 1 century ago, people didn't know that the universe is bigger than our galaxy and that it isn't static. Well, this idea is actually weird because it's founded on false grounds. It's true that astronomers and theoretical physicists of past centuries didn't use terms like redshift, cosmological constant, Big Bang, or galaxies as understood today, but they did define an existing universe beyond the Milky Way and did talk about a common original cause of all heavenly bodies, which generated a dynamical process of cosmic evolution. This conference is mainly dedicated to the work Slipher did here in Flagstaff. In the next sessions, we will extensively discuss his contribution, so I'd rather like to present another point of view. I will put the core of the subject in a broader context, so that we could form a better opinion of the historical significance of the discoveries made 1 century ago. In astronomy, it's clear that to have any knowledge of the universe, it isn't enough to consider its actual state. Without taking into account the cosmological evolution, it's impossible to understand anything at all. In other words, we need to look at the phenomena from a historical perspective. We need to look at the past in order to develop appropriate theories. Well, history of astronomy has the same demands as astronomy itself. My work as historian focuses on the macrostructural conceptions about the universe and the images made from them in modern Europe. The goal of my recent work is to trace back the processes that made possible a progressive shaping of theories, leading to the current state of things. It's from this standpoint, from this contextualization of astronomical theories in a deep time perspective, that I want to talk today about the expansion of the universe. The radial velocity of the Andromeda Nebula, as called in Slipher's times, have several implications in a more general realm. As usually occurs in science, a very specific event, in this case, the measurement of the shifts in the spectrographic lines of the galaxy, trigger broader consequences, since each phenomenon is required to be explained within a general theoretical framework. Therefore, from Slipher's analysis of the photographic plates taking here the Lowell Observatory. Later astronomers deduced that our universe is expanding, that is, that the distance between distant galaxies increases with time. To give observational evidence of the rapid motion of a very distant object implies, on the one hand, the identification of the autonomous behavior of such object. I mean, autonomous with respect to our galaxy. And on the other hand, it implies a dynamic concept of space. I want to present a brief historical overview of these two aspects and the essential notions associated with them. Namely, first, the awareness of external independent systems associated with the concept of structure. And second, the dynamics of space, or in other words, the idea that space and expanding space is shaped by evolution over time. First, structure, a universe composed of many galaxies. The general opinion usually tends to assume that Slipher's confirmation of the independent motion of Andromeda and Hubble's discovery of its distance with respect to us laid the foundation stone of the awareness that other galaxies exist. They actually achieved, for the first time, conclusive measurements, which implied irrefutable evidence of the actual existence of other galaxies. However, it isn't true that only after these discoveries, a general awareness of the complex structure of our universe arose. In fact, this idea was progressively conceived in Europe, especially in an intense way, from the 16th century onwards. The most famous historical precedent is the so-called island universes hypothesis, forerunner of the galaxies, the first outline of which is generally credited to Kant. The German philosopher was one of the leading figures in shaping the ideas of the modern cosmic structure. However, it's important to note some structural misunderstandings associated with him. Many authors still repeat that the term island universe or universes comes from the book Universal History and Theory of Heaven, written by Kant in 1755. This assertion is wrong in a double aspect. Kant neither used the term island universe in his text, nor did the idea behind it start with it. Kant actually talked about other systems similar to the Milky Way, even describing them as rotating disks shaped like flat surfaces, a Fläche in German. But he referred to them using different expressions, like similar systems, ähnliche Systeme, Systemata, world systems, Weltgebäude, Weltsystemen, world orders, Weltordnungen, heavenly host, Himmelsheere, or solar systems, Sternensysteme. Kant used many words for mentioning what we now call galaxies, but none of them was island universe. It corresponds to a later incorrect attribution, more appropriate to denote the debates in astronomy in the second half of the 19th century and the beginnings of the 20th century, culminating in the famous Great Debate of the 1920s. It's in the latter that authors, in fact, explicitly use the expression island universe. The word island, Insel in German, is indeed used by Kant sometimes in this book, but for referring to a real island, Jamaica, or as a metaphor applied to planets without inhabitants. He said that the regions of the sky without any inhabited planet are like deserts or islands, Guste oder Insel, he said, in the ocean of the universe. When talking about that, he didn't mean other galaxies. So we can assert that Kant talked about the concept of island universes, but it isn't accurate to attribute him this specific term. The second misconception concerning the island universes consists in attributing to Kant the first outline of a theory leading to the recognition of independent systems different from ours. Actually, this misconception sometimes goes further, and his name is the only mention within the prehistory of galaxies. Fortunately, this issue has been sufficiently refuted by secondary literature. The German philosopher gave a very precise description of the universe structure according to our current picture of the cosmos. It's in his accuracy which lies his historical significance, and not in simply talking about this topic in a very early time, since many other authors have dealt with this subject by Kant's time. For instance, we should remember, as Kant himself stated in his book before describing his cosmic model, that his ideas start from Thomas Wright. He considered that the English astronomer didn't draw proper conclusions from his hypothesis, and thus Kant wanted to further develop them, as he did. Notwithstanding, Kant followed what he thought were some of the most important ideas of Wright's worldview. I specify what he thought because Kant didn't read any book by Wright, only a report in a journal. This personal interpretation and the subsequent additions were in fact the most accurate outline of the picture of the universe before the arising of contemporary astronomy. What did Kant find in the report on Wright's book? Thomas Wright didn't say that the Milky Way is a flat disk, but rather that we perceive it in this form. According to him, our galaxy was like the crust of a perfect sphere, which due to optical effects appeared to us as a faint circle of light. We are supposedly located in the middle of this crust, embedded into it, and therefore we have the optical illusion of being in a plane. In the slides, we can see the images Wright provided to explain this visual effect. Kant was inspired by this view and took a step further. He asserted that it isn't an optical effect, but that our galaxy has indeed a disk shape. More precisely, that is a rotating elliptical disk. The other crucial idea taken by Kant from Wright was that the nebulae we see in the sky are other systems similar to our galaxy. Wright wrote, I quote, that there are also other luminous spaces in the starry regions, not unlike the Milky Way. Moreover, he specified that these luminous spaces are in fact the cloudy stars or nebula seen in the sky, giving examples of some of the nebula he could observe through his telescope. In the middle of the 18th century, Kant defined a universe composed of many distant nebulae that resembled the Milky Way in several aspects: its form as a flat, rotating elliptic disk, its structure, including planetary systems, and also the possible and probable presence of many inhabited planets. This example illustrates very well how the awareness of a universe composed of galaxies of a similar nature to the Milky Way didn't arise with Hubble, nor at his time. More than 1.5 centuries before, Europeans had already defined the cosmos in these terms. Before the 20th century, theoretical physicists had defined the universe structure in right terms. The main shift 1 century ago consisted in giving an observational confirmation of previous hypotheses. Thanks to the discoveries made by Slipher and later astronomers, became a fact what theoreticians had described earlier. Moreover, in spite of the crucial role played by authors like Wright or Kant in the history of astronomy, we cannot forget that when they wrote their key books, the topic of the existence of many systems similar to ours was very popular, really in fashion, and already encompassed many diverse formulations, hypotheses, published books, detractors, and defenders. A significant case within this context was the popularization of the idea of the plurality of worlds, thanks to the French author Bernard Le Bovier de Fontenelle and his famous scientific novels, Conversations on the Plurality of Worlds. I devoted my PhD thesis to the careful analysis of all editions of this book, from its first release in 1686 until the present. Fontenelle didn't talk about nebula or galaxies, nor confer importance to the role of the Milky Way in the structure of the universe. But he insisted time and again that the cosmos is much more complex than the solar system and goes further beyond it. Following Descartes' theory of vortices, he argued that many planetary systems do exist independently with respect to our system, and also that they have similar characteristics to it. I show you in this slide the single engraving appearing in the first edition of Fontenelle's Conversations, made by the Spanish artist Juan Olivar. The solar system is represented in the center of the scene, including the known planets at that time, that is, encompassing only as far as Saturn. The solar system is surrounded by many planetary systems with the same basic structure, that is, a central star, a variable number of planets, and possibly satellites. This unusual representation of the universe, together with the refined literary style of Fontenelle's text and his powerful ideas, contributed to the wide spread of this worldview among scientists and intellectuals, and maybe more importantly, also among the general public. While the ideas of an infinite, or at least of a very complex universe, were a constant in European traditions since antiquity, it wasn't until Fontenelle that they reached a broad popularization. Many authors echoed these topics after him. At Kant's time, to talk about the complex structure of the cosmos was a very recurrent topic, often being tackled in astronomical treatises. Astronomers had assumed that the physical world is composed of a plurality of worlds, as they called at that time these other planetary systems beyond the known universe. In fact, when Kant went a step further and suggested that the existence of other galaxies, he still used the term world to refer to them. Notwithstanding that this topic has a very long tradition in Europe, we must recognize the merit of Kant's theories in giving a precise description of the elements composing the universe structure, which was maybe the first really accurate explanation before the factual discovery of galaxies. When Hubble, after Slipher's contribution, gave unquestionable proofs for the existence of distant galaxies, he didn't initiate a new paradigm in macrostructural theories of the universe. Rather, he demonstrated that this long tradition in European astronomy was right, thus closing the debates around this topic. From then on, once the grounds of the universe structure were definitely confirmed, astronomy could concentrate on analyzing with much more detail specific phenomena taking place in it. Before then, galaxies were an hypothesis based on observational evidence, and sometimes based on pure theoretical or even speculative physics, without solid arguments to defend it. After the discoveries of 1 century ago, it became finally possible to infer the physical size and mass of distant galaxies, provided that we have the cosmological parameters allowing us to translate redshift into distance. Second, space and time, expansion and evolution. Apart from dealing with the universe structure, scientists in modern Europe also consider the effects of shapes changing with time. That is to say, they did talk about cosmic evolution. Mainly from the 17th century onward, cosmology was introduced in science as a crucial component of astronomical hypotheses. In past centuries, scientists didn't use terms didn't use the terms, nor the scientific facts we consider today. However, they understood that the universe isn't static, but instead that it's in constant change and motion. Let's see a couple of examples to get an idea about the notions around cosmic evolution before the advent of contemporary science. The main reference in cosmology within the modern period was, of course, the French philosopher and theoretical physicist René Descartes. Before him, it was usual to talk about the origin of the universe, but always according to a religious perspective, mostly centered in the Bible and the book of the Genesis. In the 17th century, Descartes initiated the modern trend of taking cosmology into consideration within a strict scientific perspective. He configured the grounds of his physics in Le Monde, a text written around 1630, but withheld from publication until 3 decades later due to his anxiety about the persecution of Galileo. The entire book is dedicated to the physical laws that explain the formation of the cosmos, a topic that was very original at that time. Descartes assumed that God created the first matter, describing it as, I quote, the hardest and solidest body existing in the world. After the creation, God shook this compressed, dense matter. From then on, he didn't play any further role. Instead, he let the universe evolve alone. By the shape of God, the primordial dense matter divided into different parts, according to Descartes' words, like pieces exploding when a stone is broken. Due to the continuous motion generated after this shape or explosion, the parts collided with the closest ones, triggering subsequent divisions and mergers in a kind of chain reaction. As a result, matter acquired the most diverse forms. According to Descartes and other authors from the 17th and 18th centuries, the universe, be it finite or infinite, went beyond the solar system. Let's remember that the solar system was at that time the spatial reference at the large scale. Moreover, for these authors, the whole cosmos had a common origin. They explain how the universe evolved from a primordial dense matter, which by its essential motion was expanding and forming the different systems. At this point, the hypotheses from the modern period focus on explaining the formation and evolution of each system and don't apply the particular conclusions to the whole existing space. They didn't emphasize expansion in itself, but this idea was implicit in many cosmological hypotheses. These scientists explicitly said that each system is getting bigger, but they didn't refer to the general expansion of the universe. Let's note that expansion at that time involved basically that the physical space is becoming bigger with the passing of time. Another important author in the history of modern cosmology was the Swedish scientist Emanuel Swedenborg. In the 18th century, he described an evolving universe, giving a personal interpretation of the Cartesian vortices. He referred to the cosmos as an active space with two basic components, figure and motion, or geometry and mechanism, what we now call structure and evolution. He explained the formation of the solar system, emphasizing that in the beginning, all its matter was condensed around the sun, like a crust. And I quote, "In the course of time, it removes itself farther and farther, and in so removing itself, occupies a larger circle of space. The tendency of the crust," he said, "is to fly off to a greater distance." Since his model was based on the idea of vortices, according to Swedenborg, the expansion of the matter within the solar system continues in a spiral motion until it reaches the border of the solar vortex. Then this matter collapses, with the border of the vortex and forms a kind of belt that rotates around the sun. This ring continues evolving and condenses to form planets and satellites. Swedenborg considered different cases for the latter evolution. It could subside inwardly or exteriorly toward another system, but in general, it should reach equilibrium with the volume of the vortex. 1 century later, the French astronomer Pierre-Simon Laplace took the basic ideas from Swedenborg's cosmology, but now without considering the vortex hypothesis. Instead, he explained the expansion and evolution of systems by gravity. According to him, matter was originally of a hot and fluid nature, a zone of vapors, as he said. Its rotating motion caused the expansion of the space, progressively moving away from the central star. This increasing distance of the particles provoked a process of cooling down and condensation, from which planets and satellites were formed. Laplace describes how the velocity of the molecules within the system isn't the same. The molecules more distant with respect to the central star have a greater velocity than the closest ones. The French astronomer shaped the nebular hypothesis of planetary system formation in the 19th century, when science had consolidated many of the cornerstones, later fundamental for the development of contemporary theories. At the end of the 16th century, there began in Europe a long process of defining a new picture of the cosmos that culminated with the work of observational astronomers one century ago. During the 17th, 18th, and 19th centuries, a series of scientists gave partial explanations about the structure and evolution of the universe that agree in their most basic principles with our current understanding. At that time, it was mainly about hypotheses remaining in a theoretical realm. The real merit of Slipher and the later astronomers lay in giving for the first time in history conclusive observational evidence that demonstrated the validity of earlier hypotheses. It was indeed the culmination of many centuries of investigations. Therefore, from my point of view, the crucial role of Slipher, Hubble, and other contemporary scientists wasn't only their initiation of a new period in astronomy, that is, in relation to future events. Rather, their relevance takes on more meaning in relation to the past, in terms of bringing to a close the deliberations in astronomical theories during more than 3 centuries of scientific endeavors. Thank you for your attention.
So, any questions?
Lucia, do you have any evidence that Slipher or Hubble was interested in?
Could you talk a bit louder, please?
Yes, sure. Any evidence that Slipher or Hubble were interested in Kant or Swedenborg or Descartes?
No, I can answer this question, but it's interesting that we were saying yesterday all of these drawings about Mars and the channel of Mars, and I mean it belongs to a long tradition. It's not like something unusual at the time to think about this thing, as it comes from this tradition of the plurality of worlds, of these earlier traditions, and Slipher was surrounded with these people and with these ideas, and I don't know if he know Kant or all of these things, but yeah, I mean somehow it's a tradition that is remaining until this time.
Isn't there a danger that you could cherry pick the historical evidence so that we take the modern view and then we look back in the past for people who guessed the modern view correctly? Probably there were a lot of ideas that were completely wrong and incorrect. And we need to be quite careful that we weren't just looking for the ones that happen to get the right answer by luck.
I think that's an exceedingly important point. I mean, you showed us how things developed, and that's fine, but I think there would be a danger to think that there was just one stream leading up to our present knowledge.
Yeah, of course, for each author, these kind of theories played a different role. It's also a lot of things to discuss about it. Also the role of religion, the goals they had when he defined the universe at that term and in that terms. But yeah, we cannot avoid to think that it's indeed an immanent tradition in the history of astronomy. I mean, it wasn't the only point of view, and for example, Descartes didn't emphasize like an idea of the Big Bang or something like it. It's something like he can mention in a sentence, but he didn't confer importance. For him, it wasn't important at all. When we, from now, read these books, say, wow, but he mentioned this idea. I mean, of course, we are telling the story from our point of view, and for these authors, yeah, I mean, an example is Descartes, but other examples, maybe that they mentioned that, but for them, it wasn't important because he wanted to do other things or their goal were different. But yeah, this is but anyway, I think the main idea of this complex universe was, and every author was talking about it. This general idea is not like a footnote or something. It was really the main discussion, the main topic discussed.
That's fascinating. In your research, could you draw any connection between some of these European writers and Edgar Allan Poe, who also wrote a famous essay in the early 1800s where he visualized an expanding universe in very general terms? But I'm curious as to whether there's any evidence that he was influenced by some of these writers and things.
No, I haven't studied Poe so precisely, but there is a interesting parallel development between scientists and theoreticians and literature and artists and all this field of popularization of astronomy. And I'm paying, in this case, more from an artistic, I mean, from the visual art point of view, I'm paying attention because they really play a very important role in the evolution of these theories. There are also, during the 17th century, for example, I read some books about popularization of astronomy, talking about Newton and everything, but also including poems of famous poets at that time, talking about the same ideas, but from a free, So it's, this evolution is always in parallel and influencing.
You have mentioned it, but I think it deserves even stronger emphasis. The role of gravitation, Newton. This was exceedingly important, I think, for Kant also, because Laplace evidently, Newton they had now discovered the driving motor, and I think that was very important in the evolution.
Yeah, in this period, especially in the 18th century, it was always this struggle between Descartes and Newton. And because Descartes was, of course, saying that now gravity is mechanical laws, it got shape, it's motion. Then came Newton and said, no, it's gravity. And then all the European community were against Descartes and saying, no, he was wrong, we must pay attention to this new idea, this is right. But how he explained Newton, I mean, explained the motion of the planets and so on. But the problem was that, of course, due to political reasons, Descartes was really, how do you say? Sorry? Yeah, pushed away of the discussions. And what I try to do also is to mix again these two traditions, because the two are so important within this evolution. I mean, without Descartes, we can't understand anything at all, because he thought about these macro-structural conceptions about the universe. He gave this general view that in many points were not so false, his conceptions. Of course, gravity failed, but yeah, combining these 2 points of view, these 2 traditions, we can get another idea.
I'm wondering what was the earliest use you found of the words island universe. I thought it might have come from William Herschel, but I looked very carefully and I couldn't find it there.
Yeah, I still have to do this task. I was trying to do it, but I didn't have time enough. And the earlier I saw it at the end of the 19th century, I don't remember exactly the date. But it was like in the second half of the 19th century. But I must do it because later.
I think it turned up. I have it in the head, but the term doesn't come up. You know, it's already old age. It was a German. He made big encyclopedic work. He described nature.
Humboldt?
Huh? Humboldt. I think Humboldt was the first one.
Your question.
Yeah.
Another question over here.
Yes. To what extent did Giordano Bruno fit into this whole notion of the plurality and how that affected others in Europe at the time?
Yeah, the case of Bruno is interesting because, of course, he was the main reference for these authors, but it was so dangerous in the 16th century to refer to the works of Bruno that nobody did that. I mean, for example, Descartes was the main figure in describing and defending a universe composed of multiple systems. He didn't say it's an infinite universe, but he said, let's say that it's undefined or undetermined. No?
Typical scientist. Right?
Yeah, we cannot. But for example, yeah, I mean, in the case of Descartes, he didn't want to publish his first book because of the problems of Galileo. So, and the second time he wrote a physical treatise, he put much more emphasis in God and God is the first cause, and to make it politically correct.
Yes.
So it wasn't allowed at all to talk about Bruno, and that this tradition in the 17th century and 18th century. I mean, of course, Bruno should be there, but nobody talked about it.
One more question from John.
Just coming back to Newton and gravity, I think Newton is perhaps a good example where the greats of the past didn't anticipate the modern picture, although could have done. So Newton was asked by Bishop Berkeley, what would the future state be if you filled infinite space with matter? Now, from the modern point of view, we'd say, obviously, it's effectively a collapsing universe. But Newton, I think, failed to suggest anything like that. His insistence was that matter would fragment into clumps. But the idea of this body of clumps globally in motion, he had the chance to say that they would be, but didn't take it.
Yeah, and also the thing with Newton is at that time was perceived in very different ways. I mean, of course, the English speaker scientists were defending Newton, and he talked explicitly our hero, our national hero. But, for example, in France, it was the age of the Enlightenment, and some of them, most of them in the first half of the 18th century, didn't consider Newton because he was talking of God and what is this mysterious force causing the motion. So, and for example, these French enlightened intellectuals did defend Descartes as the real modern representant of modern science, while Newton was, by French people, considered like something between religion and science, a kind of strange theories. So this.
Okay. Okay, well, thank you again, Lucia. It's been great.